Hello guys, how are you today? So today I'm going to be explaining the Chapter 6 course revision questions of AP Chemistry. Now for this periodic we have Chapter 5, Chapter 6 in Fundamentals and Chapter 1 in Interactions and Compounds. So I already did Chapter 5 from last term. You can find it on my playlists or on my courses under AP Chemistry. Now without further ado, let's start with the very first question. List the postulates of the kinetic molecular theory of ideal gases. So I'm going to start one by one. The first one is that a gas is made of tiny particles of negligible volume. So the first thing we need to know is that the gases have what? They have a negligible volume. This is the very first thing. So gases have a negligible volume compared to what? Compared to the volume of its container, right? Or in other terms, we can call these gases what? Point masses. So again, the first postulate states that the gas particles have a negligible volume compared to the volume of its container, or we can call them what? We can call them point masses. We'll move on to question number 2. Postulate number 2. What is postulate number 2? It's that the particles don't exert any force, whether that's attraction or repulsion. So I'm gonna do attraction or repulsion on each other. So the particles don't exert any force on each other. They don't attract each other, they don't repel each other. So this is the second postulate. Now we move on to the third postulate. What's the third postulate? It's that the particles move randomly and undergo perfectly elastic collision. Yes, this we took it in physics, in mechanics, but we're not gonna go into depth in chemistry. We just need to know that the randomly moving particles undergo perfectly elastic collision. So the randomly moving particles undergo elastic, I forgot to put perfectly, so they undergo perfectly elastic collision. So the third postulate is that the randomly moving particles undergo perfectly elastic collision. Now, the last and final postulate, which is the fourth one, I'm going to write it in pink. The average kinetic energy, this means average kinetic energy, okay, of the particles is directly proportional to their absolute temperature. That means their temperature that must be in Kelvin. What does this mean? This means if I multiply my average kinetic energy by 2, that means my temperature is multiplied by 2. If I divide my temperature, of course, that must be in Kelvin by 2, I will divide my average kinetic energy by 2. So this is what it means. So that's question number 1 done. We'll move on to question number 2. What does it say? It says some oxygen gas at room temperature and 1 atmosphere pressure. So this is my pressure, was compressed from 400 centimeter cubed to 50 centimeter cubed. Assuming that the temperature remains constant, calculate the new pressure of the gas. So what is the equation that I used over here? First of all, I should know the general equation, which is P1V1 over T1 is equal to P2V2 over T2. This is what most cases come as, and this is what we need to have memorized. P1V1 over T1 equals P2V2 over T2. Here they told us that the temperature remains constant, so I can cancel them out, and I'm going to be left with P1V1 equals P2V2, right? So now I start pressure 1, which is 1, times volume 1, which is 400, is equal to pressure 2, which I need to find, times volume 2, which is how much? Which is 50. So then if I'm calculating for P2, I'm going to get what? I'm going to get that P2 is 400 over 50, or 1 times 400 over 50, which is what? Which is 8 atmospheres. Whatever you start with, or whatever is initially here, should also be the same, where it should also be the same over here. So that's it for question number 2. We'll move on to question number 3. What does it say? It says a sample of oxygen gas at 25 degrees Celsius. Whenever we have temperature in degrees Celsius, we change it to Kelvin by adding 273. So this is going to be 298. And 1 atmosphere, this is my pressure. Okay, had a volume of how much? Of 400 centimeter cubed. So this is temperature 1, this is pressure 1, this is volume 1. The gas was cooled. So now what did they do? They changed the temperature. So what are you going to do? You're going to do minus 25 plus 273. So that's 248 Kelvin. So that's temperature 2. Assuming the pressure remains constant. Okay, that means pressure 1 is equal to pressure 2. Calculate the new volume. So volume 2, they want us to find it. What is the general equation we need to know? We know P1 V1 over T1 is equal to P2 V2 over T2. We know that the pressure is constant, so we can cancel that out. We get V1 over T1 is equal to V2 over T2, but of course your temperature needs to be, oh sorry, there we go. But of course your temperature needs to be in, let me see, can I bring this down? Okay, like this. But of course, your temperature needs to be in Kelvin. So it's going to be volume 1, which is 400 dot, over temperature 1, which is 298, is equal to volume 2, which I need to find, over 248. So then volume 2 is equal to 400 times 248 over 298. And then you're going to get an approximate answer of 333 centimeter cubed. Okay, that's it for question number 3. We'll move on to question number 4. What does it? Okay, question number 4. Now we start with the number of moles. Number of moles of O2. Okay, so I'm going to call this N1. At a particular temperature and pressure had a volume, okay, so this is volume 1 of 400 centimeter cubed. What volume will be occupied by 1 mole, so this is what N2, of H2 gas at the same conditions. So first of all, we have what? We have the same conditions, meaning the same temperature, the same pressure. We know PV is equal to nRT. If temperature and R and pressure are all constant, then I can say that the volume over N is going to give me what? It's going to give me a constant value. Or I could say what? I could say V1 over N1 is equal to V2 over N2. So now, what does this mean? This means if I want to find the volume, I'm going to take volume 1, which is 400 centimeter cubed, over 298. How did I get that? Oh, sorry, not 298. That's a mistake. Over 0.50, here, the number of moles, is equal to volume 2 over 1. So I put it on the calculator, and what am I going to get as an answer? I will get 800 centimeter cubed. So my answer is 800 centimeter. But it is wrong. Why? Because I need to take it to the least amount of significant figures. If I'm comparing 400 to 0.50, here I have 3 significant figures. Oops, why did I erase? Here I have what? Here I have 2 significant figures. That means I need to change this to 2 significant figures. So I'm going to take it as 8.0 times 10 to the power of what? 2 centimeter cubed. This is another way, or the proper answer, okay? We're going to move on to question number 5. What does it say in question number 5? A mass of helium gas at room temperature is placed in a cylinder fitted with a piston, and the piston is adjusted so that the volume is 250 milliliters. This is volume 1. And its pressure is this much. This is what? Pressure 1. If the piston is raised so that the volume becomes 350 milliliters, this is volume 2, what will the new pressure of the gas be, assuming that the temperature remains constant? So again, P1 V1 over T1 is equal to P2 V2 over T2, right? So what can I cancel? I can cancel the temperature because it stays the same. So P1 V1 equals P2 V2. So P1, what was P1 for me? 0.50 times V1, which is 250 milliliters, is equal to P2, which I need to find, times 350 milliliters. So P2 is equal to what? P2 is going to be equal to 0.5 times 250 over 350, which is approximately 0.36 atmospheres. Perfect. We'll now move on to question number 6. What does it say in question number 6? So now we move on to question number 6. What does it say? Calculate the volume that will be occupied by this much moles, this is N, of oxygen gas at temperature 27. You need to change it to Kelvin, so 27 plus 273, which is 300 Kelvin, right? And 1 atmosphere, this over here is what? This over here is our pressure, assuming ideal behavior. So that means we'll be using PV equals nRT, and they told us use R as this. So whenever they say assuming ideal behavior, that means we need to use PV equals nRT. So our pressure in this scenario is 1 atmosphere times the volume, which we need to find, is equal to 0.50 times 0.080 times 300. So our V is going to be equal to 0.50 times 0.08, right? times 300. So all in all, it's gonna give me what? It's gonna give me 12 liters or 12 decimeter cubed. So this is what this is. This is our volume. We're gonna move on to question number 7. What does it say in question number 7? Calculate the mass m of hydrogen gas that will occupy a volume of this much. So this is our volume V. This is our temperature in Kelvin, so that's 300 Kelvin. And 1 atmosphere, this is our pressure. And I believe we should take R as 0.08. So I'm going to take R as 0.080. They want us to find the mass. PV equals nRT. N is mass over molar mass. So PV is equal to M molar mass times R times capital T. I want to find M alone, right? So what am I gonna do? I'm gonna change the equation a bit. I'm gonna move this here and I'm gonna move these there, right? And I will get that M is equal to PV capital M over what? Over R times T. So I'm looking for the mass M, right? M is gonna be equal to the pressure, which is 1, times the volume, which is 2,500 centimeter cubed. You need to change it into decimeter cubed, so you will divide by 1,000. So that's gonna be 2.5 times what? Times the molar mass of hydrogen gas. Hydrogen gas is H2, so you're gonna multiply it by what? By 2 over R, which is 0.080 times T, which is 300. So you put it on the calculator. 1 times 2.5 times 2 over 0.080 times 300. This will give me an answer, which is approximately 0.21 grams. Now we'll move on to question number 8. What does it say in question number 8? Question number 8. How many molecules? Whenever they say molecules, you very simply need to do the number of moles times Avogadro's number of CH4 are present in a cylinder of volume 20 centimeter cubed at 27 degrees Celsius and 380 millimeters of mercury. So first of all, we need to find N. I know that R is going to be what? It's going to be 0.080. I need to find N by using PV equals nRT. So I need to change all of the values to what? To their suitable units. So for example, I'll change 200 into what? I'll change 200 into 200 centimeter cubed into decimeter cubed by dividing by 1000. So I get 0.200. I'll add 273 to get it in Kelvin, so 300 Kelvin. And I'm going to divide by 760 millimeters of mercury to get it in atmospheres. So I'm going to get 0.500 atmospheres. So PV equals nRT. PV over RT is equal to N. So the pressure that we have, what's our pressure? Our pressure is 0.500 times. So times now my volume, which is 0.200 over R, which is 0.080, times what? Times 300. So I put it on my calculator. 0.500 times 0.200 divided by 0.080 times 300. You will get 4.17 or 4.2. Let's take it because if we want it to the correct significant figure. So you get 4.2 times 10 to the power of minus 3 moles, right? So now how do we find the number of molecules? Number of molecules is the number of moles, so 4.2 times 10 to the power of minus 3 times Avogadro's number, so 6.02 times 10 to the power of 20. So what's it gonna be? It's gonna be 4.2 times 10 to the power of minus 3 times 6.02 times 10 to the 23. So I'm gonna get an approximate answer to two significant figures as 2.5 times 10 to the power of 21. So that's it for question number 8. We're going to move on to question number 9. What does it say? The temperature of a fixed mass of gas of volume 100 centimeter cubed, so my volume is 0.1 decimeter cubed, was dropped from 127 degrees to 27 degrees. So 127, you need to change it to Kelvin. That's 400. 27, you need to change it to Kelvin. You add 273, you're going to get 300 Kelvin. The pressure changed from 2 to 1.5. What will the volume of the gas become? So number of moles is fixed. R is always fixed. So P1V1 over T1 is equal to P2V2 over T2, right? So pressure initially was how much? Was 2 times volume 1 initially, which is 0.1 decimeter cubed, over temperature initially, which is 400, is equal to pressure 2, which is 1.5 times volume 2, which we need to find, over 300. Now you just need to do cross multiplication. You will get that volume 2 is equal to this. You guys should know how to do it based on the math. So 2 times 0.1 times 300 over 400 times 1.5. You will put it on the calculator and you will get what? You will get that volume 2 is also 100 centimeter cubed, right? sorry, it's 0.1 decimeter cubed. That means it's also what? It's also 100 centimeter cubed, okay? That means the volume does not change. Okay, so that's it for question number 9. We'll move on to question 10. What does it say? It says a gaseous mixture at 25 degrees Celsius. So directly we, actually wait, 25 degrees, let's continue reading. With the number of moles N1, 0.5, okay, of CH4, and number of moles N2, okay, or let me write N of CH4, better than N1 and N2, N of CH4 and N of O2 under a pressure of 1 atmosphere. The gases combusted according to the following reaction. So let's take the ratio. Here we have 1 plus 2, okay, and here we have 1 plus 2. So in total, if we have 1 plus 2 as a ratio for gases, okay, remember, whenever we're taking the ratio, you only take and you only deal with the gases. So here's the gas, 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 and gas. So I have one gas here. I have 1 mole of gas plus 2 moles of gas. So that's in total 3 moles of gas, compared to 1 mole of gas plus 2 moles of gas, which is in total 3 moles of gas. So we get a 1-to-1 ratio. That means whatever happens here will happen the same over here. They told us temperature is 25, it stays 25. So what will happen to the pressure? The pressure is going to stay the same. The pressure is going to be 1 atmosphere. If you want to explain it in detail, you'll say all reactants will be consumed as a mole of reactants are in the correct ratio. At the same temperature, in the same volume, the total pressure will change if the number of moles changes. But in this scenario, the temperature did not change. The number of moles did not change. So what does that mean? Oh, also the volume did not change. So what does that mean? That means the pressure is not going to change. That's why we say it is 1 atmosphere. We move on to question number 11. What does it say? It says a flask of volume 2 decimeter cubed. So this is the volume. Was found to contain 1.45. This is mass of an unknown gas, X. Okay. The pressure in the flask was 100 kilopascal. How do we change from kilopascal into atmosphere? Very simply, if it's kilopascal, you just need to divide by 101. And then you'll get your answer in atmospheres, okay? And the temperature was how much? The temperature was 25 degrees Celsius, so plus 273. This will give me an answer which is 298 Kelvin. They want us to calculate the molar mass of gas. So I have the volume, I have the mass, I have the pressure, I have the temperature, I have R, and they want me to find the molar mass. So I use PV equals an RT. Why? Because N is mass over molar mass. So pressure times volume is equal to mass over molar mass times R times T. So my pressure, which I found to be 100 over 101, I found it to be 0.99. I'm going to take it as, actually let me keep it as 100 over 101, okay? Times my volume, which is 2.00 decimeter cubed, is equal to the mass, which is 1.45, over the molar mass times 0.08206 times what? Times the temperature, which is 298. So now I'm going to change the equation. I'm going to let you guys do the changing and moving and solving and whatever. But you're going to get that the molar mass is equal to the mass, 1.45, times R, 0.08206, times 298 over what? Over the pressure times volume. So over 100 over 101 times what? Times 2.00. Okay, that's a lot of talking. So 1.45 times 0.08206 times 298 over 100 over 101. Times 2.00. Do not forget the brackets. They're the most important part of the equation. So you put it on the calculator and you're going to get an approximate answer of 18 grams per mole. So this is the molar mass M. We're going to move on to question number 12. These are really easy. What is the volume of 1.6 grams of O2 at STP? When they say STP, we directly think of what? We directly think of 22.4. Now, 1.6 grams, this is the mass. I can take the molar mass of O2, it's 16 times 2, which is 32. I will get the number of moles. I also know number of moles is equal to volume over Vm. So I just need to substitute, right? So 1.6 over 32 is equal to the volume, which I need to find, over Vm, which is 22.4. So volume is equal to 22.4 times 1.6 over 32. We'll get an answer which is equal to approximately 1.1. So approximately 1.1 liters to the correct significant figures, okay? We'll move on to question number 13. What does it say? Find the volume, oops, my bad. Find the volume in decimeter cubed of this many moles of helium gas at RTP. How do I find the volume? Volume over Vm is equal to number of moles. So volume is equal to number of moles times Vm. If it's RTP, that means Vm is what? Is 24. So volume is equal to what? Is equal to the number of moles, which is 0.25, times Vm, which is what? Which is 24. So 0.25 times 24. This will give me an answer, which is what? Which is 6.0 decimeter cubed. Okay? I'm going to move on to question number 14. What does it say in question number 14? A sample containing 2 grams, this is the mass of a gas, occupies 900 milliliters, so 0.9 liters. At STP, that means Vm is equal to 22.4. What is the molecular mass of the gas? Again, we know mass over molar mass is equal to number of moles. Number of moles is equal to volume over Vm. So I just need to substitute 2. V is 0.9, Vm is 22.4. So now I need to redistribute the equation. So if I do cross multiplication, I will get 2 times 22.4 is equal to 0.9 times m. So I move 0.9 to the other side. So I get what? I get 2 times 22.4 over 0.9. This will give me an answer which is approximately 49.8 grams per mole. So that's it for question number 14. We're going to move on to question number 15. What does it say in question number 15? Calculate the density D of CH4 at 100 degrees Celsius. Oops, I moved the thing. Wait. So density of CH4 at 100 degrees Celsius. So you need to add 273. It becomes 373 Kelvin. And pressure is 5 atmospheres. We know that the equation is PV equals nRT, but N is what? N is mass over molar mass. If I brought molar mass to the other side, I would get PV capital M is equal to mRT. What if I brought volume to the other side? I will get M over V. So PM is equal to M over V RT. M over V is what? Is density, because we know density is mass over volume. So now, what can I do? I have this new equation. I'm going to use this new equation. So the pressure, which is 5, times M, what's the molar mass of CH4? It's 12 plus 4 is equal to the density times R times T, right? So I'm going to move it down. So 373, this is T times R, which I believe they used it as what? What did they use R? They used R as 0.08206, okay? So 5 times 16 over 373 times 0.08206. This will give me an answer, which is what? Which is approximately 2.6 grams per liter. That's it for question number 15. We'll move on to question number 16. What is it? So we move on now to question number 16. 6 grams, this is the mass of a gas, exerts a pressure of 0.2 atmospheres. What extra mass should be added? Okay, this is really important. PV equals nRT. N is mass over molar mass. So what did they say? They said that the pressure changes, but volume, they said everything else stays the same. So volume, R, molar mass, and temperature, what happens to all of them? They stay the same. So now we need to have a relation with P and M. So P over M has to be equal to what? Has to be equal to a constant. So what does this mean? This means P1 M1 is equal to P2 M2, right? So now, what do we say? We say pressure 1, which is 0.20, over 6 grams is equal to pressure 2, pressure 2, they gave it to us, 0.80, over M2. How do we find M2? M2 is going to be equal to 0.80 times 6 over 0.20. This is stoichiometry. Not stoichiometry, this is cross multiplication. So 0.80 times 6 over what? Over 0.20. So this will give me M2 to be equal to what? M2 to be equal to 24 grams. But this is not what they asked us for. They said, what extra mass should be added? So 24 grams minus the initial mass, which is 6. How much will that give me? That will give me an answer of 18.0 grams. We move on now to question 17. What does it say? A sample containing 0.020 mole, this is the number of mole of NH4NO3, is heated in a 1 liter rigid vessel. This is what? This is the volume. What will be the pressure in the vessel when all ammonium nitrate decomposes at 127 degrees? This is temperature. So 127 plus 273, this is 400 Kelvin. So now, look what we're gonna do. They want the pressure in the vessel when the ammonium nitrate decomposes at a specific temperature. Now, pressure is only created by gases, so the only thing we need to look at is the gases, not in the reactants. Instead, we need to look at the products, okay? So I look at my products. I started initially with 0.020 mole of NH4NO3. 1 gives me 0.020. There's no limiting reagent because the only reactant is NH4NO3, okay? So 1 NO2 will give me 0.020 mole. 2 H2O will give me 0.040 mole, right? So now when we're talking about the pressure, we'll take the combined number of moles, which is 0.060 mole. Now I can apply PV equals nRT. So P is nRT over V. So it's 0.060 times R, which I think, let me check what they used it. They used it as 0.08206 times the pressure, times the temperature, which is 400 over V, which is 1, okay? So you put it on the calculator, 0.060 times 0.08206 times 400 over 1. You'll get an answer, which is approximately, to the correct number of significant figures, 2.0 atmospheres. So that's it for question number 17. We'll move on to question number 18. Okay, we move on to question number 18. 3 gases are pumped into 4 identical gas bulbs. That means they all have the same volume. That means if we were doing P1, V1 over T1, we would cancel the volume. Why? Because it is the same. Then the pressure in each bulb is recorded as shown in the diagram, which bulb contains the greatest number of moles. Now, I know PV equals nRT. I know volume stays the same, R stays the same. I need to find the number of moles. So I'm going to move here. So I can say that pressure over temperature, which is the absolute temperature in Kelvin, is directly proportional to the number of moles. So for each of them, I will take their pressure, I will divide it by their temperature in Kelvin, and then I will find an estimate of the number of moles. So the pressure, which is 1 atmosphere, over the temperature, which is 20 plus 273, so 293. And then, then here we have 0.6 over 60 plus 273. And then here we have 1.5 over 30 plus 273, right? What's 30 plus 273? 303. So 1.5 over 303. Then we have 1.2 over what? Over 303, which is 60 plus 273. You put it on the calculator. 1 over 293, this is 3.41 times 10 to the power of minus 3. 0.6 over 333, this is 1.80 times 10 to the power of minus 3. Then we have 1.5 over 303. This will give me a ratio of 4.95 times 10 to the power of minus 3. Then here we have 1.2 over 333, which is 3.6 times 10 to the power of what times 10 to the power of minus 3, right? So then you put it on the calculator, right? Oh, sorry, we already put it on the calculator. So now we can see that this has the greatest mole proportionality. So that means bulb C contains the most number of moles. In which bulb, A or C, is the density of gas the highest? We don't remove anything yet. We need to find density. What's the equation for density? It's Pm equals dRT. Now in A and C, they're both the same gas. That means the molar mass is the same. R is the same. We're talking about density. So you move temperature, then you can say that pressure over temperature is directly proportional to the density. What does this mean? I don't need to solve again. I already have my values, right? Right? So now what do? I take my value for A, okay? And I divide it by the value I have for C. So it's going to be 3.41 times 10 to the power of minus 3 over 4.95 times 10 to the power of minus 3, right? So I put it on the calculator. I will get an answer which is what? Which is smaller than 1. Since we have an answer which is smaller than 1, we will say that A is less dense than C. And that's it for question number 18. We move on to question number 19. What is it? Okay, question number 19. Carbon monoxide, CO gas, and oxygen, O2 gas, are placed in a rigid reaction vesicle and then heated to react. The reaction produces CO2 gas. So let us write the balanced equation. Carbon monoxide gas in addition to O2 gas will give me CO2 gas. So as you can see here, it's not balanced. How do I balance it? First of all, if I put a 2 over here and a 2 over here, it will become balanced. I'll have 2 carbons and 4 oxygen. Now part B, fill the blanks below with the particles found in the vessel at the end of the reaction. So we need to find the particles found in the vessel at the end of the reaction. First of all, I'm gonna look at the initial one over here. What do I see? I have 1, 2, 3, 4, 5, and 6 O2, right? So here I have 6 oxygen. And how many carbon monoxide do I have? I have 1, 2, 3, 4, 5, 6, 7, 8. 8 carbon monoxide. Now, how do I find the limiting reagent? Very simply, let us see. Limiting reagent, I need to find the ratio. I start first with the ratio. I take carbon monoxide, I take the number of moles. I divide it by what? I divide it by the ratio. So 8 over 2, that's 4. Now I do the ratio for oxygen. 6 divided by moles, so 6 over 1, that's 6. So which one is smaller? Definitely 4. That means carbon monoxide is my limiting reactant. So the whole equation goes based off of carbon monoxide. So if 2 carbon monoxide gave me 8, that means 1 O2 is going to give me 4 and 2 CO2 is going to give me 8. Right? And I know over here I had initially 6. So that means what am I going to have remaining of the oxygen? 6 minus 4, because I used 4, so 6 minus 4, I will have 2 oxygen remaining. So what will be formed? I will have 8 CO2, right? And I will have 2 oxygen. So I'm going to say that this is oxygen and this is carbon, okay? So then I will have what? I will have 1. So look, as you can see over here, everything here in the middle is carbon dioxide. So I have 8 carbon dioxide and 2 O2. That's it for part B. We'll move on to part C. When the reaction goes to completion, will the vessel increase or decrease? Okay, so I kind of deleted whatever I had, but in general, I had 8 plus 2, so that's 10 molecules of gas. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14, which is much greater than 10. Right? So definitely we decrease the number of molecules. So what's going to happen? So the pressure is going to decrease. Okay. We move on to question number 20. What does it say in question number 20? A sample containing 4.8 grams. This is the mass of CH4. This we can find the molar mass. The molar mass is 16. Right? And 6 grams. This is the mass of C2H6. Molar mass is 20. Is kept in one container. The total pressure is 1.2 atmospheres. Calculate the mole fraction and the partial pressure of each gas. So they want two things. They want the mole fraction of each gas. So first this, and then this, and then the partial pressure of each gas. So partial pressure of CH4 and partial pressure of C2H6. So now how do I find the mole fraction? Very simply, I just need the number of mole of CH4 over the total number of moles. So how do I find the number of mole of CH4? I need to do mass over molar mass. So the mass, which is 4.8, over 16 divided by the total number of mole, which is 4.8 over 16, plus what? Plus 6 over 20. What will I get as an answer? Let me put it on my calculator. Don't forget your brackets, they're very important. 4.8 over 16 divided by 4.8 over 16 plus 6 over 20. So this will give me an answer of 0. Oh, by the way, this is a mistake. This is 30, not 20. My bad. So you put it on the calculator. Please fix it. That's my mistake. So 4.8 over 16, right? Divided by 4.8 over 16 plus 6 over 30. What would this give me as an answer? This will give me 0.60 as the mole fraction. Now for C2H6, it's gonna be the mass, which is 6 over the molar mass, divided by, again, 4.8 over 16 plus 6 over 30. Now all you need to do is change the numerator. So now it's 6 over 30 divided by 4.8 over 16 plus 6 over 30. And it will give me an answer of 0.40. Now what you should notice is that all sum of mole fractions add up together to give you an answer of 1. Now that you have the mole fractions of each 0.60, 0.40, you multiply it by the total pressure to get what? To get the partial pressure. So 0.60 times 1.2, this will give me an answer which is 0.72. 0.40 times 1.2, this will give me an answer which is 0.48. And if you do 0.48 times plus 0.72, you'll get an answer which is 1.2, which is the original pressure. We move on to question number 21. What does it say in question number 21? A cylinder okay, contains O2 and H2 at the respective partial pressure 25 millimeters of mercury and 15 millimeters of mercury. What is the mole fraction of H2? How do we find the mole fraction? The mole fraction is quite simple. Also, the pressure fraction. There's no such thing as pressure fraction, but I call it the pressure fraction. And where you put the partial pressure of the gas, for example, partial pressure of H2, over the total pressure. So what's the partial pressure of H2? They told us it's 15 millimeters of mercury divided by the total, which is 25 plus 15. Right? So you put it on the calculator. 15 over 25 plus 15. This will give me an answer of what? This will give me an answer of approximately 0.38. So this is the mole fraction to the correct significant figures, the mole fraction of H2 in the mixture. We'll move on to question number 22. What does it say in question number 22? A rigid 8.2 liter flask. Okay, this is our volume. Contains a mixture of 2.50 moles. This is the number of mole of H2. And 0.50 moles of Cl2, the number of moles of Cl2. And sufficient argon. What does this mean? This means we also have a specific number of moles of argon. And what did they give us? They gave us the partial pressure of argon in the flask to be what? To be 2 atmospheres. They also gave us what? They also gave us the temperature as 127 degrees Celsius. So of course you need to change it into what? You need to change it into the temperatures in Kelvin. So 127 plus 273, this is 400 Kelvin. Now calculate the total pressure in the flask. The first thing I need to do is I need to find the number of moles of what? The number of moles of argon. Now, how do I find the number of moles of argon? I will use PV equals nRT. Now, my missing is N. So PV over RT is equal to N. Now, which P do I use? First of all, I should know always that the R is the same for all gases, temperature is the same and volume is the same. The only thing that differs is the pressure. They gave us the partial pressure of argon, so I'm going to do the partial pressure of argon in atmospheres times the volume over R, which I'm going to use it as, what did they use it? They used R as 0.082 times what? Times 400. I'll get the number of moles of argon. So 2 times 8.2 divided by what? Divided by 0.082 times what? Times 400. So I will get that I have 0.5 moles of what? 0.5 moles of argon. So now I have what? I have the number of moles of argon. What am I going to do? I'm going to calculate the total number of moles. It's going to be 2.5 plus 0.5 plus 0.5, which will give me 3.5, right? Now, what am I going to do? I'm going to find the mole fraction of argon. Mole fraction of argon is 0.5 over 3.5. Now this, when I do 0.5 over 3.5 times the total pressure, I'm going to get my partial pressure, which is 2 as an answer. So I'm going to move this to the other side. Total pressure is equal to 2 divided by 0.5 over 3.5. I'll get my answer as 14.0 atmospheres. That's it for part A. What do they want in part B? The mixture in the flask is ignited by a spark and the reaction represented below occurs until one of the reactants is entirely consumed. Give the mole fraction of all species in the flask at the end of the reaction. So they gave us the balanced equation. What we're supposed to do is we're supposed to find the limiting reagent. The limiting reagent in this scenario, I should have a ratio of what? A ratio of H2 versus a ratio of Cl2. What's the ratio of H2? The ratio of H2 is the number of moles of H2, 2.5, divided by the coefficient. The ratio of Cl2 is the number of moles, 0.5, divided by the coefficient. So for sure Cl2 is what? Cl2 is going to be completely consumed, so it's the limiting reagent. Now I start doing, if one Cl2 gave me 0.5, one H2 will give me 0.5, 2 will give me 1.00. What does this mean? This means from the reaction I consumed 0.5 moles of H2, I completely consumed the 0.5 moles of Cl2, and I formed 1 mole of HCl, right? So what does this mean? If I had originally 2.5 moles and I use 0.5, I'm left with 2.00 moles. That means I have 2.00 moles of H2. On top of that, I have 1.00 mole of what? So this is H2 of HCl gas. And of course, don't forget that the argon. Argon is a noble gas. It's not going to react. So we have 0.500 moles of argon. Now we can find the mole fraction of each. So let's find the mole fraction of H2, mole fraction of HCl, and the mole fraction of argon. First of all, what am I going to do? I'm going to take 2 divided by the total, which is 3.5, 1 divided by 3.5, 0.5 divided by 3.5, and you put it on the calculator, and you'll get for each of them what you'll get for each of them, the mole fraction. So that's it for question 22. We'll move on to question 23. What does it say? A 20 milliliter, so 20 milliliter, that's 0.02 liter sample of neon gas was collected over water at temperature 27 degrees. 27 plus 273, that's 300, my bad, how do I go up? There we go. That's 300 Kelvin. The pressure in the tube was 1.32 atmospheres. Assume the vapor pressure of water at 27 degrees is 25 millimeters of mercury. Calculate the number of moles of neon gas collected. So what we need to do is we need to find the pressure of neon, and then we'll be able to find the number of moles of neon. The pressure of neon is equal to the total pressure minus the pressure of water, okay, or H2O. I should write it in chemistry terms. The pressure of H2O. So the pressure of neon, which I'm looking for, is equal to the total pressure in atmospheres minus, if it's in millimeters of mercury, I divided by 760, right? So now it's going to be 1.32 minus 25 divided by 760. I'll get an answer, which is what? Which is 1.29 atmospheres. This is the pressure of neon. Now I can apply PV equals nRT, right? So N is equal to PV over RT, right? So the pressure is 1.29 times the volume. The volume is always the same for any gas. They all take the same volume. Divided by R, what did they use R as? They used it as 0.08206, right? Times 300. You put it on the calculator. So I put it on the calculator, 1.29 times 0.02 liters divided by 0.08206 times 300. So what will my answer be? My answer is going to be approximately 1.05 times 10 to the power of minus 3 moles. Move on to question number 24. When do real gases behave most ideally? We have a few cases, like a few things we should state. Okay. So real gases, I'm gonna write it and then I'll say it. So I wrote the answer. Real gases behave most ideally when their particles exert minimal forces. This again goes to the postulates, okay, on each other and occupy the least volume. This is usually the case for the lightest gases at a high temperature and a low pressure. I remember in the AMS, they said which gas deviates the most from the ideal gases. So deviates means goes are not as related to, you know. So if it deviates the most, that means it's not related to it at all. So you need to say the opposite. You need to say a low temperature and a high pressure. Whereas if they say least deviate, high temperature, low pressure. Okay, you have to pay attention to the wording in chemistry. So this is, let me check how much we have. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 37, 38. I'm not going to do the top questions, so we have only until question 28 and we're done. Perfect. So the graph below shows the plot of PV against P for an ideal gas under constant temperature at 3 non-ideal gases X, Y, and Z. Okay, now let's go down. What does it say? Which of the following would be gas X? Gas X is a straight line passing through the origin. That means it's for sure the lightest gas as it's the most ideal. After that, we have Y. Y deviates from ideal gas, but not that much. So it does not deviate too much. So it should be a kind of in between. So the middle gas, like the middle between comparing of the weights. Last but not least, we have what? We have gas Z, so it deviates the most, so it must be what? It must be the heaviest gas. So gas X should be the lightest gas. When you do the molar mass calculations, you will see that H2 is the lightest gas. We'll move on to question 26. The Maxwell-Boltzmann distribution curves of 4 different gases at the same temperature are shown below. Which property of the different gases can be compared using the plot? So let's see the plot. They said number of molecules versus molecular speed. So we cannot compare number of molecules and molecular speed. Instead, what we can compare is what is the molar masses. Why? Because we know that the heavier something is, the slower it moves. So that means this is the heaviest, right? And then the lighter something is, the faster it moves. That means this is the lightest. So from these, we can find what? We can find the molar mass. We'll move on to question 27. What does it say? The Maxwell-Boltzmann distribution curves of a gas at two different temperatures are shown on the plot below. Which is the higher temperature, temperature 1 or temperature 2, and why? So temperature 2 should for sure be greater than temperature 1. Why? Because the average molecular speed, so the average molecular speeds at temperature 2 is greater than that at temperature 1. So that's why temperature 2 must be greater than temperature 1, because the more you increase the temperature, the faster the molecules are to move. So we move on to question 28. What does it say? Question 28. The molecules of a certain gas X of formula NX H2X move 4 times as slow as the molecules of hydrogen gas at the same conditions. Let us see. They told us to calculate the molar mass and calculate the value of X. I'm going to do it all in one solving. What is the equation we learned from before? We know that the velocity of the lighter gas over the velocity of the heavier gas is equal to the square root of the molar mass of the heavier gas divided by the molar mass of the lighter gas, right? So I'm going to start. What's the velocity? What did they say? They said NX H2X moves 4 times as slow. What does this mean? This means hydrogen gas is faster than NX H2X. This is N, okay? How did I know? Because they said this moves 4 times as slow as the molecules of hydrogen. That means NX H2X is heavier than what is heavier than H2. H2 has a molar mass of 2. So now let us calculate the molar mass of NX H2X. So I'm going to call this X, right? This is Vx, Vh2. This will give me an answer of what will give me an answer of 4. Why? Because H2 is 4 times as fast as NX H2X. So H2 over NX H2X should give me an answer of 4. So I'm going to call this all X, okay? So now what do? I square both sides. I get 16 is equal to X over 2. So then X is equal to what? X is equal to 32. So what does this mean? This means that the molar mass is 32. Next step. Molar mass is 32. What does this mean? This means I have 14 times X because the molar mass of nitrogen is 14. Plus 2 because I have 2 times hydrogen times X. So what does this mean? 32 is 16X. X is then 2. So just like that, we found the molar mass and we found the value of X. We'll move on. Oh, and what's the equation? Sorry, my bad. The equation is N2H4. Okay? We'll move on to question 29. What does it say? 5 identical balloons under the same conditions contain each of the following gases: C2H6, SO2, O2, CO, and neon. Which balloon contains the greatest mass of gas? You just need to find the molar mass, okay? And then using Avogadro's theorem that the number of moles times the molar mass will give me what will give me the mass, you just need to say that using Avogadro's hypothesis, number of moles times molar mass will give me the mass. So the one with the biggest, since they all have the same number of moles, the one with the biggest molar mass will give me the greatest mass. So thus it will be what? It will be SO2. Compare the average kinetic energies. Always, if they're under the same conditions, then the average kinetic energies are the same for all of them. So they all have the same kinetic energy, the same average kinetic energy, because they are all at the same temperature. Which gas is expected to deviate the most? Definitely the heaviest gas, which is what? Which is SO2. Why? Okay. SO2 will deviate the most. How do you explain this? SO2 will deviate the most from ideal behavior because it has the largest molecules and the largest electron cloud size, right? So its particles occupy the largest spaces and thus have the strongest IMF between them. So thus it's gonna be harder for them to undergo ideal behavior. 6 hours after being filled, all balloons have decreased in size. Predict which balloon would be the smallest. We know that the lighter the gas, the faster it travels, the faster its speed. That means the lighter a gas, the faster its effusion rate. So which is the lightest gas out of all of them? That would be neon. So neon would be the smallest. Why? Because you say the lighter gases, the faster its effusion rate. Neon is the lightest, so it will diffuse fastest out of the balloon, and as a result, the size of the balloon that contains neon will be the smallest. We'll move on to question number 30. What does it say in question number 30? Dry ice, solid CO2, changes directly to gas at a room temperature. This phase change is called what is called sublimation. Is energy released or absorbed? Now, logically speaking, if I have a solid, let's say this is my solid, right? if I have a solid, I'm gonna have strong intermolecular forces. If then it becomes a gas, which does not have too strong intermolecular forces, what did we do? We broke the bonds. In order for us to break the bonds, what do we need to do? We need to absorb heat, or absorb energy. So energy is absorbed during this change, okay, in order to break the intermolecular forces between solid CO2 molecules. And that's pretty much it for 30. We'll move on to 31. Liquid A has a vapor pressure of 58.3 kilopascal. Liquid B has a vapor pressure of 220 kilopascal. Which liquid is expected to have a higher boiling point? First of all, what's the definition of a vapor pressure? Very simply, a vapor pressure corresponds to how much vapor is created under the same conditions and under the same conditions. So if the two gases are if the two liquids are under the same conditions, the vapor pressure just states how much liquid will transform into what? Into a vapor. So what does this mean? The one with the higher boiling point should have what? Should have the lower vapor pressure, because it needs more temperature in order for it to turn into a gas, right? So that means A is my first answer. Now, how do you explain this? The liquid with lower vapor pressure, liquid A, is expected to have a higher boiling point as it needs to be heated, okay, before its vapor pressure becomes equal to the atmospheric pressure. What can be concluded about their intermolecular forces? That means A has stronger intermolecular forces than B, right? Why? Because stronger intermolecular forces cause it to have a higher boiling point and thus a lower vapor pressure. We move on to question 32. What does it say in 32? Explain why Br2 is a liquid at room temperature and pressure, while F2 and Cl2 are both gases under the same condition. Very good question. First of all, we take Br2, we take F2, we take Cl2, and we compare the forces. They are all molecular. So molecular, I'm just going to say for all of them, they're all molecular, non-polar, so the only force acting is LDF. Whenever we have LDF, what do we compare? We compare the electron cloud size. Br2 has a greater electron cloud size than F2 and Cl2, right? So bromine has a greater electron cloud size than F2 and Cl2. It's more polarizable, right? And because it's more polarizable, what does this mean? This means that the London dispersion forces, or the induced dipole, the IDID, right? Is strong, okay, making it a liquid at the same, like at room temperature and pressure, whereas F2 and Cl2 are gas, okay? We'll move on to 33. Answer the following question. What does it say? This is the concentration of NaCN, concentration of MgBr2, concentration of C2H5OH, and concentration of HF. Which solution has the lowest electrical conductivity, and explain? So first thing, we're not going to relate anything to the concentration. The concentration is just there to tell us that it's a solution, you know? But now we need to think on terms of what? We need to think on terms of the type of bonding. This is first ionic because this is an A plus, Cn minus. MgBr2, this is MgBr2 is also ionic. It's Mg2 plus 2Br minus. C2H5OH, this is not ionic, this is molecular. It's an alcohol, molecular. And then last but not least, we have HF. Now HF is not ionic, but because it has what? It has hydrogen bonding. Because what does the hydrogen bonding only occur on oxygen, nitrogen, and fluorine? Here it does have, but at the same time, it's not that much of hydrogen bonding. It's more molecular, you know? Anyways, hydrogen bonding. That's why when you put it in water, it will form it has the same bonds of water, so that's why it dissolves, right? So that's why there will be two ions, the H plus and the F minus. So yes, this is also kind of ionic. So the only one that is not ionic is the molecular one, and it has the lowest electrical conductivity because all ionic can conduct electricity. We'll move on to question 34. What does it say? The table below shows physical properties of solids. Fill in the table below. Part A. CaO, type of intermolecular forces. There is no conductivity of solid. there's no conductivity. Yeah, there is a conductivity of the liquid, right? So there's no conductivity as a solid, but there's conductivity as a liquid. It has a really high melting point and a really high boiling point. So I'm gonna say that it's ionic. Because ionic bonds are really strong, so it's gonna have a really high melting and boiling point, and it's gonna only be conductivity as a liquid. Okay, it's only gonna have conductivity as a liquid. Now, what's the type of solid structure? It's gonna have ionic crystal lattice. Now, C, graphite. Graphite has conductivity as a solid. It's not known conductivity as a liquid. It has a really high melting point and a really high boiling point. Now, we know that graphite has what? Graphite has covalent and London dispersion forces. So, covalent and London dispersion forces. How do we know it's covalent? First of all, because carbon should usually form 4 covalent bonds with the other carbons. But in graphite, it only forms 3, and it has one single free electron that will cause the sea of electrons, that will cause the electricity to be able to flow, right? And it has a bunch of layers, and these layers are connected by the London dispersion forces. And what do you call the structure? You call it a giant covalent structure. We move on to I2. What does I2 say? What's I2? No conductivity as a solid, no conductivity as a liquid, really low melting point, really low boiling point. That means the only force it has is the London dispersion force, right? And what's the structure? The structure is simple molecular. We'll move on finally to Fe. What does it say in Fe? Conductivity solid, conductivity liquid, high melting point, high boiling point. That means it's what? It's a metal. So metallic, right? And what's the structure? It's a metallic lattice. So that's it for question part A. What does it say in part B? What does it say? Why does CaO have a higher melting point than KCl? This is Ca2 plus and O2 minus. This is K plus and Cl minus. If you check on the periodic table, if you remember from like the very first chapter we took in AP Chemistry, Ca2 plus, if you look at it and you compare it with K plus, you will see that Ca2 plus has what? Has a smaller atomic or ionic radius. So smaller ionic radius. Whereas for O2 minus, and you want to compare it with Cl minus, for sure O2 minus has what? Has a smaller ionic, because they're not even on the same period. So the smaller ionic radius. What does this mean? If they have a smaller ionic radius, right? The forces are going to be stronger according to which law? According to Coulomb's law. So you're right. According to Coulomb's law, right? You need to say it. I think I noticed his name wrong. According to Coulomb's law, the electrical force of attraction between Ca2 plus and O2 minus are stronger, okay? Requiring more energy to be broken. Why? Because the ions carry double the charge of K plus and Cl minus. So basically, what does Coulomb's law state? K Q1, Q2 over R squared. If you increase the charge, okay? Like you're increasing the charge, what's gonna happen to the force of attraction? The force of attraction is gonna what? It's gonna increase. Now we'll move on to part II. Why do KCl and CaO conduct electricity only in the molten state but not in the solid state? First of all, you need to say the ions forming the compound are free to move in the molten state. So in the molten state, the ions are free to move, and thus the electric current can flow through them, right? But in the solid state, the ions have fixed positions in the lattice and cannot move freely. This is why it conducts electricity only in the molten state, but not in the solid state. We'll move on to question 35. What does it say? Consider the following solids: KCl, SiO2, Cu, and S8. Which is most likely to be soluble in water? Definitely KCl. Justify your answer. KCl is the only ionic compound, and usually they dissolve in water, forming strong ionic dipole interactions. Whereas SiO2 is a giant molecular structure, Cu has a metallic structure, and S8 has a simple nonpolar molecular structure. None interact strongly with water, and so they are what they are: insoluble. Is the resulting solution a good electric conductor? Explain your answer. I have KCl. It will split into K plus and Cl minus. Now, because of this, okay, It will form a solution that's a good electrical conductor due to the mobile ions. The ions are able to move and conduct the electricity in the liquid solvent, which allows the transfer of electricity within the solution. That's it for part B. We'll move on to 36. Oh, we have 36, 37, 38, and we're done. Let's go. Name and compare two types of alloys using diagrams and giving examples of each. I'm gonna draw regularly. What I'm gonna draw? This. Okay, and I'm gonna explain. We have two types of alloys. We have the interstitial alloy, where we fill in the gaps or the interstices, right? And so the host atoms, they are not affected, but they are occupied by other atoms of smaller sizes, and thus this will be an interstitial alloy. Now, a substitutional alloy is when you remove or you substitute the atoms, right? Like you substitute the host atoms by the other metal atoms. This is called a substitutional alloy. So, for example, something like this. This is a substitutional alloy. That's it for 36. We'll move on to 37. What does it say? Question 37. Consider the phase diagram of the pure substance S when answering D. Before we do anything, let's understand. You should know that each line represents something. Usually, the line more to the left is for solid. So here, this is for the solid. The line in between is more for what? Is more for liquid. So I think I'll put it down. The line in between is more for the liquid. And then the line that exceeds to the right is more for the what? Is more for the gas. So now that I have everything, I can do what? I can start answering the question. At what is the normal boiling point of S? When they say normal, they're talking about what? They're talking about 1 atmosphere. Now, boiling point needs to be in the gas region, so it needs to be touching the gas graph, so I'll get 140 degrees Celsius. The triple point is a very easy point. You just see where they all intersect, and it will be at minus 10 degrees and 0.5. They said, in what state does S exist at a temperature of minus 15, okay, under atmospheric pressure? So you continue it, you will see it's more where, you will see it like here, you see, this is atmospheric pressure, this is minus 15. You will see it's where you'll see that it's closer to the liquid. So that means it's a liquid, more likely a liquid, okay, at a temperature of minus 15 degrees under atmospheric pressure. Now, which of the following is S most likely to be? So now you need to think out, like, you need to think in your mind, is this at room temperature condition? What's room temperature condition? We know that S, okay, we're talking about it like we're thinking about it in room temperature, is most likely to be a liquid, right? So let's say like room temperature for me is over here. And I'm gonna extend it. I will see that still my line is closer to where my line is closer to the liquid. That means my S is supposed to be what is supposed to be liquid. You should know that neon, oxygen, I2 and not I2. Neon, oxygen, and H2S are gases, okay, at room temperature and pressure. I2 is a solid, and the only one left is H2O2, which is what? Which is a liquid. I don't think I read that properly. Which is a liquid at room temperature and pressure. So that means my answer is what? My answer is H2O2. We move on to question 38, and then I'm done for this video. Diamond and graphite are both allotropes of carbon. Define the term allotropes. Allotropes, they are what? They are different forms of the same element in the same state, right? Allotropes are different forms of the same element in the same state. Graphite is soft and brittle, made of carbon. Diamond is crystalline and hard, made of carbon. So these two are allotropes. They said, explain why graphite is soft and brittle and why carbon is hard. Sorry, why diamond is hard. First of all, graphite looks something like this. It has like a hexagon, like a small tiny hexagon over here. I know it's not accurate, but I'm just drawing whatever, you know. So this is what it looks like. It looks kind of something like this, right? And it has what in the middle? It has gaps. These gaps are held together by what? They are held together by London dispersion forces. London dispersion forces are one of the weakest forces, so that's why graphite is soft and brittle. Whereas when it comes to a diamond looks like this. You have 1 carbon here, then 2, 3, 4, right? And then from here you have 1 down, and then 2, 3, 4, right? And then from here you go 1 down, you have 2, and these two connect to each other, 3 and 4. And then I think I activated my series, sorry. And then you go down from here, right? And then how do you go? You go 1, 2, 3. So this is a diamond structure. As you can see, they are all held together by what? They are all held together by covalent bond. There's not a single London dispersion force. Covalent bonds are strong. So that's why diamond is crystalline and hard. Why? Basically, how do you say this in words? The forces between the layers of carbon and graphite are weak. They have LDF forces. They can be easily broken, and the layers of graphite can slide past one another when a force is applied. Diamond, on the other hand, forms a structure where every carbon is covalently bonded to 4 other carbon atoms at the corners of a tetrahedron. This results in a very hard and rigid structure. And in part C, they told us to draw a sketch of the structures. I already drew a sketch. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful day.